carries no birth certificate tucked into its glowing surface, no cosmic registry listing its formation date. There exists no ancient logbook floating through space, no faded photograph of infant starlight wrapped in hydrogen clouds. When astronomers examine HD 140283, they observe an object that has existed across nearly the universe's entire history. The star itself reveals nothing plainly, offering no declaration about forming shortly after the first stellar generation ended. It simply radiates energy into the darkness, maintaining its ancient vigil without speaking directly to curious observers below. Astronomers must therefore employ their most refined techniques, gathering evidence from light, distance, motion, chemistry, temperature, and brightness. They assemble these fragments into the most careful estimate that current physics and measurement technology can possibly provide. Determining a star's age resembles examining an old structure by studying its wood, foundations, accumulated dust, and construction methods. For certain stars, this task proves easier than for others, though easy remains a generous word in astrophysics. When a star belongs to a cluster, astronomers gain a useful advantage because cluster members typically form together. These stellar siblings originate from the same enormous gas cloud, meaning they share roughly the same age initially. Some members burn small and cool, while others blaze large and bright across the galactic neighborhood for millennia. Plotting cluster stars on a brightness temperature chart reveals which members have already departed the main sequence of hydrogen fusion. The point where stars begin leaving this stable phase is called the turnoff, and it serves astronomers well. A young cluster still contains massive, hot, luminous stars, burning steadily on the main sequence throughout their lifetimes. An old cluster has lost those short-lived giants because they already evolved onward or died completely long ago. That method works beautifully for groups, especially globular clusters orbiting the Milky Way like ancient lanterns around a city. But HD 140283 sits isolated in space, a field star traveling alone through our neighborhood of the galaxy. Without a cluster providing siblings for comparison, astronomers cannot simply place Methuselah among its stellar family members born simultaneously. They must understand the star itself through luminosity, temperature, composition, mass, and evolutionary stage, then compare everything to models. These stellar evolution models are essentially long, careful calculations of how stars with different masses and compositions should evolve. The first major clue comes from brightness, but not the apparent brightness that human eyes would notice here. Apparent brightness shows how bright a star looks from Earth, while true brightness or luminosity reveals actual energy output. Those quantities differ significantly, just as a candle close to your face might outshine a distant street lamp visually. Before astronomers can judge a star's real brightness, they must know its distance with considerable precision and care. This explains why the distance to Methuselah mattered so much to the entire age calculation and subsequent interpretation. If you know how far away a star sits in space, you can convert its apparent brightness accurately. For nearby stars, one elegant method of measuring distance is parallax, employing Earth's orbit as a baseline measurement. Hold your finger before your face and observe it with one eye closed. Then switch eyes suddenly. Your finger appears to jump against the background, not because it actually moved, but because you viewed it differently. Astronomers perform something similar, using Earth's orbit around the Sun, observing a nearby star from different positions months apart. The star seems to shift slightly against more distant background stars, and that tiny shift reveals its distance. The smaller the shift, the farther away the star must be from our solar system's observing position. With HD 140283, Hubble's fine guidance sensors measured this tiny shift with great precision, less glamorous than imaging nebulae. A better parallax meant a better distance, and a better distance meant a better luminosity calculation for the star. A better luminosity meant a better placement on the stellar life chart, which in turn meant a better age. Once luminosity is known, astronomers also need the star's temperature, estimated from color and spectrum, the light's rainbow spread. Hotter stars shine more blue-white, while cooler stars shine more red-orange across the electromagnetic spectrum for observers. But with an object like Methuselah, astronomers examine the spectrum carefully, looking at absorption lines carved into starlight. Those lines reveal both temperature and composition, like fingerprints printed across a rainbow rather than left on glass. The composition proves especially important for ancient stars, since HD 140283 is metal-poor compared with the Sun. In astronomy, metal means almost everything heavier than hydrogen and helium, which still feels like astronomy pranking chemistry slightly. Iron, oxygen, carbon, calcium, magnesium, silicon, all count as metals in this context, regardless of their periodic table classifications. The early universe was mostly hydrogen and helium, with heavy elements forged later inside stars and scattered widely. Methuselah's low metal content is one of the strongest signs that it formed before the galaxy became heavily enriched. But metal-poor chemistry does not by itself give an exact age, only indicating the star is very old. It resembles seeing an antique chair and knowing it is not from last week, but needing expertise to decide further. To refine the age, astronomers compare the star to theoretical models known as isochrones, curves showing where stars appear. Place a real star on the chart using its temperature and luminosity. Add its composition, and you see which age fits. For a star like the Sun, still comfortably on the main sequence, this can be difficult and imprecise. A middle-aged main sequence star changes slowly, so its properties do not reveal its age sharply or clearly. Subgiants are more helpful because they have begun leaving the main sequence as their core hydrogen runs low. HD 140283 is a subgiant, which makes it a particularly valuable ancient star for scientific study and age determination. It has reached the stage where its age is written more clearly in its current state than ever before. That does not mean the answer becomes simple, as stellar models must include many pieces of complex physics. They must account for nuclear reaction rates, the way energy travels through the star, pressure and temperature of interiors, the star's chemical mix, the amount of helium, and subtle processes such as diffusion all matter for accurate modeling. Oxygen is especially important for HD 140283's age estimate, because oxygen abundance changes how the models behave internally. A small change in the assumed oxygen abundance can shift the estimated age by a meaningful amount across time. When astronomers say Methuselah is about this old, plus or minus that much, they are being honest about ingredients. Uncertainty is not ignorance, but measured caution. The difference between saying, "I have no idea," and "somewhere between these points." In astronomy, a range is often a triumph when the object is hundreds of light years away and billions old. Being able to narrow its age to within hundreds of millions of years is not failure, but astonishing precision. It resembles estimating an ancient candle's age from another town by analyzing its flame's warmth through a keyhole. With Methuselah, the result became famous because the age estimate came out so close to the universe's known age. Around 14.5 billion years, plus or minus 800 million years. Sounds awkward when the universe itself is roughly 13.8 billion years old. This is where many people first hear about the star and imagine a paradox forming in cosmic history. But the uncertainty range matters, because if the estimate has a margin of error, the star can still be younger. It is not a genuine contradiction, more a warning light saying, "Please check the assumptions carefully," for everyone involved. Astronomers did check again, looking at the distance, the temperature, the oxygen abundance, the physics in the models. The star did not overthrow cosmology, but sharpened the conversation about early stellar formation and chemical evolution timeframes. That sharpening is valuable, because very old stars are independent checks on the history of the universe itself. Stellar astronomers estimate the ages of the oldest stars using completely different tools from cosmologists studying the microwave background. If the oldest stars all came out much older than the universe, that would be a serious problem. If they come out slightly younger or close within uncertainty, that gives confidence that the broader picture is consistent. Methuselah sits right near that boundary, which makes it exciting for astronomers studying the earliest stellar generations. It resembles a very old witness whose testimony must be handled carefully because it concerns the first few minutes. The more carefully scientists measured Methuselah's distance, brightness, temperature, and composition, the more the apparent paradox softened into acceptance. The star was not really older than the universe, just very, very old, close enough to the beginning. That is one of the lovely things about this story, beginning with what sounds like a contradiction, but opening. It opens a doorway into how science actually works, with measurements improving and uncertainties shrinking over careful decades. A strange result is not thrown away just because it is inconvenient, nor blindly accepted because it is exciting. Science at its best is not a person shouting, "I have the answer," but a room full of people. The age of this ancient star, pressing against the cosmic edge, reminds us that the oldest things require our most. The universe cannot be younger than objects it contains, a logical requirement as fundamental as bricks needing walls. Stars must form after space, matter, and time exist to support their nuclear fires, burning steadily onward. When Methuselah's early age estimates approached 16 billion years, astronomers faced not a magical paradox, but a measurement puzzle. The universe's age of 13.8 billion years comes from multiple independent lines of cosmological evidence converging. Cosmic microwave background radiation, expansion rates, and matter distribution all point toward the same rough timeline for existence. If Methuselah truly exceeded that age, either stellar physics or cosmology required fundamental revision of established principles. But the careful answer involved neither dramatic revolution nor embarrassing retraction of published scientific claims about ancient stars. Instead, the resolution demonstrated how uncertainty ranges, refined measurements, and honest error bars make science stronger rather than weaker. Error bars represent not weakness but integrity, showing how precisely scientists know what they claim to understand. When researchers say Methuselah is 14.5 billion years old, plus or minus 800 million years, that range matters profoundly. The star could actually be 13.7 billion years old, comfortably younger than the universe, within measurement uncertainty. That little phrase, plus or minus, does tremendous work, turning an apparent paradox into a confirmation of careful methodology. Without error bars, numbers gain false confidence, making perfectly respectable stars appear to violate causality without justification or reason. Methuselah lives in that narrow zone where stellar physics, cosmic history, and measurement uncertainty all intersect meaningfully together. The distance matters enormously because without knowing how far away the star sits, astronomers cannot determine luminosity. Without true luminosity, they cannot place it precisely on evolutionary tracks, showing where stars of given ages should appear. Hubble's fine guidance sensors measured parallax with exceptional precision, sharpening the distance estimate considerably from earlier ground-based observations. Sharper distance meant sharper brightness calculations, which meant better placement on the Hertzsprung-Russell diagram, organizing stellar properties systematically. But even with excellent distance measurements, the age still depended heavily on other ingredients, like chemical composition. The star sits close enough to help astronomers tremendously, but old enough to guard some secrets quite carefully. One cannot watch a star age in real time, since human civilization spans only microseconds of stellar lifespans. Astronomers see one frozen moment in an enormous life, stretching across billions of years of gradual evolution. To understand that moment, they compare observations with theoretical models, predicting how stars should change over time. It resembles understanding that acorns, saplings, and oak trees represent different stages without watching one tree for centuries. Astronomers build stellar evolution models, calculating how stars of given mass and composition should evolve gradually through time. Oxygen abundance became especially important for Methuselah's age determination, because oxygen affects internal opacity and evolutionary rates significantly. The amount of oxygen in the star influences models used to determine how quickly it evolved away from stable hydrogen burning. Change the oxygen abundance slightly, and the inferred age can shift by hundreds of millions of years. That may sound enormous, but on a 13 billion year timescale, it determines whether the star politely remains younger than the universe. Different stellar atmosphere models handle oxygen lines differently, and weak spectral features require careful analysis to measure accurately. Diffusion processes over billions of years may have altered surface composition from original formation values gradually and systematically. Some elements settle deeper while others rise, meaning today's visible composition may not exactly match the star's birth chemistry. For an ancient star, that matters, because models must reconstruct original composition to determine formation age accurately and reliably. It resembles trying to understand an old recipe after someone quietly moved spices around 13 billion years ago. Convection in stellar outer layers adds another layer of complexity, because moving plasma affects heat transport and surface properties. Stellar models handle convection using parameters that approximate extremely complicated physical processes with simpler mathematical representations of reality. For the Sun, researchers calibrate these parameters because our star is close and extensively observed across many wavelengths. For an ancient metal-poor subgiant, correct assumptions become less obvious and more dependent on theoretical choices about physics. If models treat convection slightly differently, predicted temperature and luminosity at a given age may shift noticeably enough. Once again, small differences matter, because Methuselah is being compared directly with the universe's own measured age. This explains why Methuselah's age has been discussed, revised, and re-examined for years by multiple research teams independently. The star is not difficult because astronomers are careless, but because it sits precisely where precision matters most. If a star is clearly 5 billion years old, uncertainty of several hundred million years is interesting but not alarming. If a star is estimated at 14 billion years old, the same uncertainty becomes central to the entire story. It determines whether the star seems comfortably younger than the universe, or slightly too old at first careless glance. Methuselah inhabits that narrow zone where every measurement choice, every model assumption, every spectroscopic detail carries weight disproportionate. Distance improvements helped enormously, but oxygen abundance, diffusion modeling, and convection treatment all contributed to resolving the apparent paradox. Multiple research teams approached the problem from different angles, using different stellar evolution codes, different atmosphere models, different assumptions. Gradually, the consensus shifted toward ages that, while extraordinarily high, no longer exceeded the universe's age, beyond reasonable uncertainty. The star transformed from an apparent contradiction into a powerful confirmation that early star formation began remarkably quickly. The resolution demonstrates that science advances not through dramatic revolutions alone, but through patient refinement of difficult measurements. Methuselah did not overthrow cosmology, but tested whether stellar physics and cosmic history fit together consistently across time. The uncomfortable early estimates forced astronomers to examine every assumption, every measurement, every calculation step with exceptional care. Better parallax from Hubble, improved oxygen abundance measurements, refined stellar models, and honest uncertainty treatment all contributed to resolution. The paradox softened, not because scientists ignored inconvenient data, but because they treated difficult evidence with appropriate caution. This is science at its best, neither blindly accepting surprising results nor dismissing them out of defensive convenience. A room full of researchers quietly saying, "Let us check that again," produces more reliable knowledge than confident declarations. The star remains extraordinarily old, among the oldest well-studied objects whose age we can measure with any precision. That great age carries profound meaning, because it constrains when long-lived stars could first form after the Big Bang. If Methuselah is more than 13 billion years old, first enrichment and low-mass star formation occurred remarkably early. The star becomes a timestamp for the young galaxy, saying, by this point, the universe had already made heavier elements. Not instantly after the Big Bang, but early enough that low-mass stars formed and survived until now. That statement connects one faint subgiant in Libra to the first generations of starlight illuminating the early cosmos. The age of the universe from cosmology and ages of oldest stars answer related but distinct questions about time. Cosmology asks how long the universe has been expanding from its early, hot, dense state since the beginning. Stellar ages ask how long this particular star or cluster has existed since it formed from collapsing gas. There should be a gap between those numbers because stars formed after the universe began, not simultaneously. If the oldest stars are just slightly younger than the universe, that tells us star formation began very early. If they were much younger, that would suggest a longer delay between the Big Bang and first star formation. If they seemed older, that would point to problems in measurements, models, or both, requiring careful investigation. Methuselah helps us understand not only the total age of the universe, but the schedule of its first major events. This proves especially important now that telescopes observe very distant galaxies from surprisingly early times in cosmic history. The James Webb Space Telescope found galaxies existing only a few 100 million years after the Big Bang. These observations show that structure formation in the early universe was active and perhaps more efficient than simple models. Ancient stars in our own galaxy offer a complementary view by showing surviving evidence from early cosmic history. Distant galaxies show early cosmic history directly through old light that traveled billions of years to reach us. Nearby ancient stars show surviving evidence from early times through old objects we can study in exceptional detail. One method looks across space and time simultaneously. The other carefully reads fossils still present nearby today. That balance proves valuable, because understanding the universe's age requires looking both outward and inward, both far and near. We study the oldest light in the universe, stretched into microwaves across all space, carrying information from recombination. We study distant galaxies whose light began traveling when the cosmos was young, still assembling its first structures. We study old clusters around the Milky Way, ancient white dwarfs cooling in darkness, metal-poor halo stars drifting. Each method has difficulties and assumptions, but when they begin agreeing, they create a stronger story together. A useful comparison is a courtroom, but a very calm one, with less shouting and more collaborative examination of evidence. The age of the universe stands as the question before the court, requiring multiple independent testimonies for resolution. The cosmic microwave background gives one testimony, expansion rate measurements provide another, and ancient globular clusters stand up clearly. White dwarfs speak through their cooling rates, metal-poor stars like Methuselah through their chemistry and evolutionary stages. The judge, probably a patient statistician with excellent coffee, listens to all of them and looks for consistency. No single witness needs perfection, because strength emerges from the pattern these independent measurements create when considered together. Methuselah's role becomes special because it represents an individual star in our neighborhood, not just a cluster. Globular clusters provide group ages, but HD 140283 lets astronomers study one ancient star in exceptional detail. Its distance, brightness, temperature, chemical composition, and evolutionary stage have all been measured with unusual care over decades. Because it is a subgiant, its age proves more accessible than that of many main-sequence stars. Because it is metal-poor, it links directly to the early universe through its chemistry and formation history. Because it is nearby, its measurements can be more precise than those of many ancient stars farther away. It is not the only old star, and it may not hold a simple, permanent title as oldest. But it remains one of the best-known ancient benchmarks, a standard against which other measurements are tested. The word benchmark is useful here, because a benchmark is not just a record holder for competitions. It is something used to test other things, to calibrate instruments, to verify that methods work correctly. Methuselah helps test stellar evolution models by providing a well-observed, metal-poor subgiant whose properties are known precisely. If models cannot explain it without making it older than the universe, then the models need refinement. If changes in oxygen abundance, diffusion treatment, or distance measurements bring the age into agreement, models become more credible. The star also tests the connection between stellar physics and cosmology, asking whether our understanding fits together coherently. It asks whether nuclear burning at small scales and cosmic expansion at large scales can coexist peacefully. So far, with careful uncertainties, they can, though the margin is narrow enough to remain scientifically interesting. There is a deep humility in this approach, because we are trying to measure the age of everything. We use clues from light that reaches a tiny planet orbiting a middle-aged star in one ordinary galaxy. Our instruments are brilliant, but not magical. Our models are powerful, but not complete. Our numbers are precise only within ranges. Ancient stars remind us that the universe can be known, but not bullied into giving simpler answers than reality permits. We cannot demand that Methuselah give us a perfect age with zero uncertainty, free from all measurement complications. We can ask better questions, improve the measurements, and let the answers sharpen over time through collaborative scientific effort. That is a very different attitude from pretending certainty where none exists, and it is slower but stronger. Maybe that is why the story feels right for a quiet night, because the oldest stars do not rush. They have spent billions of years shining while galaxies formed, planets gathered, and life appeared in at least one small corner of space, around unremarkable stars in ordinary galaxies everywhere. They ask us to slow our own thinking, to accept that cosmic truth is assembled from many measurements, to appreciate agreement when it appears, to understand that a number like 13.8 billion years is not simply dropped from the sky, fully formed, but the result of many lines of evidence converging after decades of careful work by thousands of researchers. The universe has an age, not because someone guessed boldly, but because many clocks, cosmic and stellar, have been read carefully and compared systematically by the scientific community worldwide. Those clocks are still being read, with new observations improving distances, and new stellar models refining ages. New surveys find more metal-poor stars. Astroseismology lets astronomers listen to stellar interiors, and better spectra reveal weaker chemical lines in faint, ancient objects throughout the galaxy and beyond. Even disagreements can be useful because they show where our understanding needs work, where assumptions need testing. Methuselah's apparent age problem was not a failure, but a signpost, pointing toward the precision needed when measuring objects. It pointed toward careful treatment of distance measurements, chemical abundances, and stellar evolution physics in the metal-poor regime. Ancient stars help us test the age of the universe not by giving one simple answer, but by standing as witnesses against impossible timelines that cannot be reconciled with physical law. They say the universe must be older than us, that early star formation happened quickly, that first heavy elements entered later stars soon after the Big Bang ended. They say the Milky Way began assembling its old populations near the dawn of cosmic history, when the universe was young and chemically simple. When their ages line up with the age inferred from the cosmic microwave background, they give us more complete confidence that the universe's great clock is being read correctly by multiple independent methods simultaneously. Methuselah, faint in Libra, belongs to this family of cosmic clocks that astronomers use to cross-check cosmological models. It is not a loud clock that ticks in ways we can hear, but it burns, shifts, and slowly evolves according to physical laws governing stellar interiors everywhere in the cosmos. Its age is read through distance, luminosity, chemistry, and models that encode our understanding of how stars work. Its usefulness comes from being close, old, metal-poor, and just evolved enough to reveal its timeline more clearly than many other ancient stars that remain on the main sequence. In its quiet way, it helps hold the universe accountable, not by challenging the Big Bang, but by confirming the story must make room for stars like it. Ancient survivors, born very early, yet still younger than the cosmos that made them, provide independent confirmation of cosmic history. And so we come back gently to that faint point of light in Libra. Not a great beacon, not a star dominating the sky, not a dazzling object forcing every eye upward the moment night arrives each evening. Just a small, old star, modest in appearance, easy to miss, and yet carrying one of the longest stories. Methuselah HD 140283 has followed us through questions of distance, chemistry, motion, age, and the early Milky Way's assembly. Now it leaves us with something quieter than a puzzle and larger than a fact, something that lingers. It leaves us with a feeling for time. Not just time as a number, or time as something divided into seconds and calendars and phone alarms, arriving too confidently at inconvenient moments when we are finally falling asleep. But time as a deep physical history, something written into starlight, into atoms, into the slow life of a galaxy, and into the small human moment in which we notice it all around us, and ask questions about our cosmic context and origins and future. When we began, Methuselah seemed almost impossible. A star so old, it once appeared to press against the age of the universe itself, like an unwelcome guest arriving too early to a party that has not yet started properly. That idea had a wonderful kind of strangeness to it, the kind that makes you pause and look twice at something you thought you understood. Could a star really be older than the universe? And if so, what would that mean for everything we thought we understood about cosmic history and the Big Bang and the formation of structure? Of course, the careful answer is no, because the universe must come first, providing space, matter, gravity, and time before a star can gather itself from gas and begin to shine steadily across billions of years, while everything changes around it, but it endures. But the fact that Methuselah came close enough to make the question feel serious is part of what makes it so valuable to astronomers studying the earliest epochs of galactic history, when the Milky Way was young. It did not break the universe, but it made us check our clocks, measure our distances more carefully, understand our chemistry more precisely, and refine our models of how old, metal-poor stars evolve gradually toward their eventual fates. It asked astronomers to measure its distance more carefully, to understand its oxygen and iron more precisely, to refine models of old metal-poor stars that formed in the early universe before the galaxy became chemically enriched through many cycles. And to remember that deep time is not read with a single number, but with many pieces of evidence, each with its own uncertainty carefully considered. That may be one of the most comforting things science teaches when we let it speak slowly, when we give it the patience and attention it deserves. A mystery does not have to destroy what we know in order to matter to the progress of human understanding. Sometimes a mystery matters because it sharpens what we know, forcing us to look more carefully at assumptions we had taken for granted, and measurements we thought were good enough, but actually needed improvement through better instruments and more careful analysis. Methuselah did not overturn cosmology, but it strengthened the conversation between stellar physics and the age of the universe, making both fields more robust through careful cross-checking of independent methods that all must agree if our understanding is correct. It reminded us that the oldest stars are not just decorations in the night, but clocks, records, witnesses, and tests of our theories about how the universe evolved from simple beginnings to the rich complexity we observe today. Their light helps confirm that the universe is old enough to contain them, that chemistry and timing and galactic evolution all fit together coherently when examined with appropriate care and scientific rigor applied consistently. If you found this quiet voyage through ancient starlight gave you a little calm, or helped the universe feel a touch more familiar and comprehensible, I would be grateful if you liked the video, subscribed, or shared this corner of science with someone else who might enjoy a peaceful drift through deep time and cosmic history. The oldest stars do not ask us to hurry, but to notice, to let their ancient light speak to something patient within ourselves, that can sit with vast timescales and feel strangely at home in the immensity of it all. So wherever you are, and whenever this moment finds you, breathe slowly, rest gently, and let the old light of Methuselah fade into the quiet behind your eyes as you drift toward sleep.